So it says, what among these three right triangles, what is the relationship among these? So let's look at these real quick. I have this right triangle, right? I have this right triangle. And then I also have this right triangle. So now, from a geometry perspective, we would say that all three triangles are similar. So we would say all three triangles are similar. And if you don't remember what similar triangles means, it means they have congruent angles. Congruent means that they're the same angles. Congruent, same angles. And proportional sizes or lengths.
I can't write anymore.
I'm recording. So what we have is, it says that all three triangles are similar. We know they're similar because they have, all three angles are the same, right? So they all have a 90-degree angle. In other words, I could put them all on top of each other like this. They all have the same top angle, right?
Yes.
And then they all have the same bottom angle. So all the angles are the same. We just proved mathematically that they have proportional lengths. In other words, those proportions are all the same, 1.3 repeating. So by definition, if they have congruent angles, the same angles, and proportional sizes or lengths, then they're similar triangles. They're not congruent because they're not all the same size, but their sizes are proportional. So then for question number 5, it says identify and label the triangles that represent the unit rate. Well, the one that represents the unit rate, this is an interesting one. I said earlier, and I just didn't like the way that Carnegie kind of labeled this, but when we talk about unit rate, we're talking about 1 in the denominator. Okay, so now there was only one triangle that had 1 in the denominator. Remember that we were comparing the height or the distance in yards. So we were comparing the distance over time. And this triangle had, at 1 second, we were 4.3 repeating yards. So I would say 1.3 repeating yards per 1 second. And that's where we get the unit rate, because we have 1 in the denominator. They were saying 4/3 was the unit rate because that was the rate at which they were measuring, so they said, well, that's their units, but it's confusing to use the term unit rate in 2 different definitions. Now, Carnegie still argues that their unit rate of measuring is 4 yards per 3 seconds. So I guess that's how, if you were to ask a pure mathematician, they would say that this was the unit rate, but based on Carnegie, they're saying this is the metric in which they measure. Well, I got back up. If you were not a pure mathematician might go for this. If you were to ask a physicist, they would say this is the unit rate. If you were to ask, I guess it would go either way. But for most of your guys' high school mathematics career, unit rate refers to having a 1 in the denominator. Okay? So now it says slide the unit rate triangle along the line. What do you notice? Well, now what they want us to do, and this is an interesting thing to see, they want us to take the original graph and slide our unit rate across it. Well, the steepness is basically the same. In other words, they want us to take the original graph and they want us to slide this along the line. So if you notice, that will always stay on the line of the graph. Do you guys see that?
Yes, sir.
So that's interesting. And then that pretty much applies for the other one. So Carnegie says, look, if you use this one, that will be the same too. Well, mathematically, we proved that they're proportional. So the ratio of the height of the triangle compared to the base of the triangle is basically proportional or the same. So the steepness will be the same. And then the last triangle, well, that's the whole darn triangle, isn't it? But if I were to slide it up, it doesn't really go off. You know what I mean?
Yes, sir.
So that's what they're trying to say. So what do you notice? It stays on the line. And that's important. Now, so another way you could say that is it's the same for any 2 points on the line. Okay. So now it says slide the other 2 triangles on the line. What did you notice? Same thing. It stays on the line. It stays in the grid. They never go off the grid. Does that make sense? So now let's move to the next page. Can I move to the next page? Okay. So now for question or page 30, it says, in the last 2 activities, you investigated the relationship using a rate of change of 4/3 to represent Jack and Jill walking 4 yards from their home in 3 seconds, or a unit rate of 4/3 yards per second. Because of this situation is a proportional relationship, the rate of change can specifically be called the constant of proportionality, represented by the variable k. In this activity, you created 3 similar triangles, each using 2 points on the line to explore the steepness of the line. By sliding the similar triangles along the line, you notice that the steepness of the line remained constant between any 2 points on the line. In any linear relationship, slope describes the direction and steepness of the line and is usually represented by the variable m. Slope is another name for rate of change. So what I want you guys to do is underline that, because that's important. Slope is another name for the rate of change. Isn't that what I've been saying the whole time?
Yes.
Now, it represents a ratio of change in the vertical to the change in the horizontal. Now, over to the side, I want you to write this. This is delta y over delta x. This is the Greek letter delta. Our letter, capital D, is based on that kind of triangular shape. Now, that just means change. We use the letter delta to represent change. So this is really saying the change in y, or the change in the vertical, over the change in x, which is the change in the horizontal. Now, the slope of the line is a constant between any 2 points on the line. You wrote the equation d equals 4/3 t to represent the distance Jack and Jill walk from home with respect to time. Let's generalize this linear relationship. So now we're getting very specific into the mathematics of it. How do we generalize that as a linear relationship? Well, let's see. We're going to go to the next page, which is page 31. And page 31 says, let y represent the dependent variable and x represent the independent variable and m represent the slope. Write the general equations for these quantities, or related to these quantities. So what they're saying is y equals mx. Remember, that's kind of like y equals kx, where k was the constant of proportionality, where this is the slope, which we were referring to as a rate of change. Now, if you ever go forward and you take calculus, calculus is all about the rate of change. It's about the instantaneous rate of change. That's all it's about. So slope is very important. How things change, when we measure things, they change over time. Sometimes it's constant, sometimes it's not. So part B says, how is the equation similar to the constant of proportionality? Well, we could think of it like this. If I take this equation, if I say y equals mx, and then I divide both sides by x, I get that the x's will cancel. Y over x is equal to m. In other words, the change in y over the change in x is your slope.